Sushruta for NEET is now available on the Google Play Store. Try it out for free.
Hello students, in our last class we have seen the electron movement in organic molecules, how the electrons and so on. When electron moves and where the double bond or single bond, that is the formation these things we have seen. Then we show the electron displacement effects in covalent bond, particularly just this thing briefly we have looked about it, and the electron displacement effect we have seen it could be a permanent effect or it could be a temporary effect. A permanent effect, if this electron displacement is permanent, we have seen that it could be because of the inductive effect or the resonance effect. Inductive effect we have seen in details, and then the temporary electron displacement effect is known as electromagnetic effect, which we will see today. And the resonance effect as well we will see today. So inductive effect we have seen in details, particularly inductive effect is a kind of, we have seen two types of inductive effect, electron withdrawing effect and electron donating effect. And with based on that we have also categorized certain chemical systems or chemical moieties in terms of the electron donating group or electron withdrawing group. Electron donating groups are said to have plus I effect and electron withdrawing groups are said to have minus I effect. And what are the implications of plus I and minus I effects in chemistry that we have also seen at some places, particularly in the effect, uh, role of inductive effect in determining acidity and basicity of a chemical system, particularly if you look at this acetic acid, that is carboxylic acid, and if electron withdrawing group is attached to this carbon, what do we see? It pulls away electron density. So it stabilizes the conjugate base, and if it stabilizes the conjugate base, acidity of the acid will increase. And if you put electron donating group to a carboxylic acid group, we see that acidity of that system decreases because of the electron donating plus I effect. And this that we can understand in terms of the stability of conjugate base again. So this is the conjugate base with the negative charge, and if electron donating group is there, it will increase the electron density here, and which the electron density increasing means the charge is intensified and the system will become unstable. So there are many some other examples also we have seen, and we have also seen the effect of electron donating and electron withdrawing groups on the basicity, and particularly if you look at the basicity of amines, secondary amines are more basic than primary amines, and primary amines are more basic than ammonia, and this is because we know that the alkyl groups have plus I effect, so plus I effect, and because of the plus I effect, we see some electron density is being put into the towards the ammonia in the nitrogen group, and so this increases the stability of the positive charge which appears because of the donation of the lone pair. And so if the ammonia, suppose ammonia is having a lone pair of electrons, it can accept a proton, so it will behave as a base. And if an alkyl group is attached, means one of the hydrogens of the ammonia is replaced with one of the alkyl groups, this alkyl group can donate certain electrons. So the positive charge that is there on that, which is actually centralized on the nitrogen, will now disperse to a bit because of the electron donating effect of alkyl group. And so the stability of the conjugate acid will increase, and the stability of conjugate acid increases, it means the basicity will increase. So now let us look into the resonance structure, resonance effect. Before understanding the resonance effect, let us first understand resonance structure and what does it mean, what are its implications. So what we see usually in organic chemistry, that a single structure for a many molecules, single structure cannot depict all of its properties. Cannot just using one single structure, you cannot understand or determine all of its properties or deduce all of its properties. For example, if you look at this benzene molecule, we see in this structure one single bond and double bond. They are all at alternate position. So what does it mean? This bond should be a double bond and double bond. So its bond length should be about whatever we see, the carbon carbon double bond length. And this is a single bond. So carbon carbon single bond should be larger in size than this carbon carbon double bond. However, what we see actually in experiments, and all the carbon-carbon bonds in benzene are of same length. It means this whatever the structure that we are showing, this with only one structure, this structure, we cannot determine the or if we cannot predetermine or guess or understand the bond length, all the equal bond length, carbon-carbon bond length in benzene. There are many other examples as well, like if you look at the aromaticity and like C2 attack in furan and pyrrole, you see that because if you look at one of the most stable one most stable resonance structure or one of the structures, we may not understand why the C2 attack of an electrophile in furan or pyrrole is preferred. And when we look at the different resonating structures, we see that the C2 position some electron density is intensified in some of the resonating structures which are also having significant contributions towards the overall hybrid, and so that those kind of electrophilic attack at the C2 position is the C2 position can be explained. Otherwise, one would expect that the oxygen in furan, actually furan is 5-membered ring having 4 carbon atoms and 1 oxygen, and there is a double bond. So suppose if I just add 1 oxygen atom here and that will furan is removed with this bond. So what will happen if the oxygen atom is here? I would expect that because of the electronegativity of oxygen here, the electron density here will decrease. But in reality, what we see the electron density here is high in the case of furan, and if that is because of one of the higher contribution of one of the resonating structures. Let us get back to this uh, thing again. So it has been seen that the single Lewis structure cannot explain the behavior of many organic molecules, such as benzene. The cyclic structure of benzene containing carbon-carbon single and carbon-carbon double bonds does not explain its characteristic properties. As per this representation, as I said just now, benzene should exhibit two different bond lengths due to carbon-carbon single and carbon-carbon double bond. So benzene should ideally, because per this structure, should have two different bond lengths for the carbon-carbon single bond and double bond, and these bond lengths should be at the alternate position. However, as determined experimentally, all the carbon-carbon bond distances in benzene are 39 picometer. 139 picometer means 1.39 angstrom, a value which is intermediate, which is between carbon-carbon single bond and double bond. And carbon-carbon single bond length is usually one, or average bond length is 1.54 angstrom, 154 picometer, and carbon-carbon double bond length, average bond length is 134 picometer, is 1.34 angstrom. But what we see, the carbon bond length in benzene, all the carbon-carbon bond lengths in benzene lie between carbon-carbon single bond and carbon-carbon double bond. And it is 139 picometer, 1.39 picometer. So it is neither a single bond or neither nor a double bond. It is actually between single and double bond. Thus, the structure of benzene cannot be represented adequately by above and only this structure. Further, benzene can be represented equally well by the equally identical structure, which is another one. Second structure, so we have this structure. This structure of benzene is shown here, and we can have another alternating structure, this one. So if you look at this alternating structure, so this is also a benzene molecule, this also represents benzene, but none of these two structures are the real structure of benzene. The real structure of benzene is something which lies between these two structures, and not only these two structures, there are many other resonating structures of benzene as well, although their contributions are very less to the overall hybrid or the real structure of benzene. Therefore, according to the resonance theory, the actual structure of benzene cannot be adequately represented by any of these structures. Instead, it is a hybrid of the two, one, two, and many more structures, which is called resonance structure, which is believed to be the real structure or the actual structure of benzene. The hybrid of all the possible resonance structures of benzene is the real structure of benzene. And so sometimes people also show this as a writing all the six-membered ring and showing the delocalization with the circuit inside that six-membered ring, showing the complete delocalization of these pi electrons. And these pi electrons are there; they are delocalized. But we have seen it between this one and two, this double bond in this structure between carbon atom one and carbon atom two, this double bond, and then this double bond between 3 and 4, 5 and 6, and the single bonds are here. However, in another structure, we see one this the bond between carbon atom 1 and 2 is a single bond. So what do we see? One can understand and one can assume that this pi electron is actually completely delocalized into the entire ring, and that is why the double bond is shifted to this position, this is shifted to this position, this is shifted to this position in this structure. So because of the complete delocalization, we also show a circle inside the six-member ring to show that to represent the resonance hybrid of benzene. So the resonance structures are also called canonical structure or the contributing structure or the resonating structures as well. So these resonance structures are also called canonical structures. Remember this term, and also the contributing structures. They are all hypothetical structures. These structures are not the real structure of benzene, as I said. They are all hypothetical structures and they do not represent any actual molecule individually. So individually, neither this nor this one represent the actual benzene molecule. In reality, the actual molecule benzene molecule is a hybrid of all the possible structures of benzene. Similarly, we see for many other organic molecules as well, in which there are many possible the possibility of resonance structures are there. So they contribute to the actual structure in proportion to their stability. So if there are many, suppose for a molecule there are many resonance structures, so what would be their contribution? So their contribution depends on their relative stability. So a structure, a resonance structure which is most stable will be having highest contribution towards the resonance hybrid, and a structure which is having having least stability will have least contribution towards the resonance hybrid or the actual hybrid or the actual molecular structure. So another example of resonance is nitromethane. This is nitromethane CH3NO2, and the structure of nitromethane we can write as this: CH3N plus, this is double bond O, and this single bond O minus. Why this could be a coordinate bond? Usually we write it as N plus and O minus, and this is because nitrogen, the lone pair, is considered to be somewhere delocalized to this position. Anyway, so what do we see in this case, and why nitrogen cannot have more than three bonds if it is a neutral position? If it is electrically neutral, nitrogen can have four bonds if it is having a positive charge. So this is what we have seen for a positive charge of nitrogen, and four bonds. From four bonds, nitrogen having 8 electrons, and so it is complete. And if otherwise ammonia, what we see, ammonia lone pair of electron is there, two electrons are there as a lone pair, and three NH bonds. So three NH bonds, 3 into 2, 6 electrons. So the 8 electrons are also there. So here this just to complete the octet of all the atoms, we can write this structure. So what do we see? This lone pair of electron or this negative charge may shift to this position, and this says pi electron of this between nitrogen and oxygen may come to now localized at this oxygen atom. So one can have alternatively this structure as well. So this lone pair shifted to this, and so a pi bond formation happens between this oxygen and this nitrogen. And so what? As we know, nitrogen cannot have more than four bonds because it cannot extend its octet because of the absence of vacant d orbitals or vacant orbitals. So what will happen? This bond will break, and this bond will also we see a negative charge over here. So, however, so it is what do we see? There are two types of nitrogen oxygen bonds in this structure. So, two types of bonds are there, one double bond and one single bond. However, it is known that NO bonds of nitromethane are of the same length. And if you look at any of these NO bonds, you will expect that this nitrogen oxygen bond should be smaller in size than NO oxygen bond length. But what do we see? And in this structure, we should expect that this nitrogen oxygen bond length should be smaller than this nitrogen oxygen bond length, because this is a single bond, this is double bond. However, what do we see experimentally, that the nitromethane has all the NO bonds in nitromethane are of the same length. So this NO bond and this NO bond, both the NO bonds are of same length, and so which is intermediate between nitrogen oxygen single bond and nitrogen oxygen double bond, and that is what it means that there is we see a nitrogen oxygen bond which is not neither a single bond nor a double bond, but it is an intermediate between these two. And the intermediate bonds usually you cannot represent clearly because we talk about the transfer of electrons, and if intermediate bond means the transfer of electron will happen, the sharing of electrons will happen in the partiality. Suppose we see that there is a partial a 1.5 bond order is 1.5. 1.5 bond order, that doesn't mean each of the atoms has shared half of its electrons with another atom, because sharing of half electrons cannot happen usually. So the actual, if you look at the structure or the multiplicity of bond, we cannot represent any of these structure. We cannot say any of these structure is the real structure. And one instead many structures together represent one real structure. And so many structure, all those many structures which together represent the real or the actual structure of the nitromethane is our resonating structure, and the actual structure which is the hybrid structure which will lie between all the resonance structures and which will have properties of all the resonance structures in the ratio of their relative stability is the real structure. Therefore, the actual structure of nitromethane is the resonance hybrid of the two canonical forms 1 and 2. The energy of the actual molecule, the resonance, which is the resonance hybrid, is lower than that of any of the canonical structure. So, what do we see? The resonance hybrid stability of the energy of the resonance hybrid, the real structure, the actual structure is always lower than the most stable resonance structure. It is even lower than the energy of the most stable resonance structure. It means the energy of the resonance hybrid is lower than any of the canonical structure or resonance structure, because it is even lower than the most stable structure. And most stable structure, resonance structure is the most lowest energy resonance structure. The difference in energy between the resonance hybrid and the lowest energy resonance structure is called the resonance stabilization energy, or simply the resonance energy. So suppose there are many possible resonance structure of a molecule, and what do we know? That it can have even a hybrid structure, the actual structure, the real, and the energy difference between the real structure and the most stable resonance structure is considered to be the resonance energy or the resonance stabilization energy. It means if the molecule has to exist in one of the resonance structural form, it will exist in the lowest energy structural form. And even that lowest energy structural form, since it is not the most stable structure, the real not the real structure is something else, which is the hybrid one of all the resonance structure. So the hybrid must be even lower than even the most stable resonance structure. The more the number of important contributing structures, more is the resonance energy. This is also a very important point. If you can write more number of resonance structures for a molecule, and for another molecule you can write fewer resonance structures, it means that the molecule with a higher number of resonance structures is usually a more stable molecule. And there are many other factors as well which affect, but usually one can consider that the greater the number of contributing in the structure, more is the resonance energy or more is the stabilization of the resonance structure, or the more is the stabilization of the actual structure. And so the molecule will be having lower in energy, it will be more stable. So resonance is significant when contributing structures are equivalent in energy. And so again, the resonance becomes significant when the contributing structures are equivalent in energy, means both the structures are having same energy. So both the structures have equal possibility to exist. And if both the structures have equal possibility to exist, stability to exist, it means resonance is more in the molecule. And so these structures, different structures, are actually resonating with each other. They are in resonance with each other, and because of the resonance with each other, they see when we assume the real structure else, which is the hybrid of the all the resonance structures. Let us look at the rules for writing resonance structures. We have written resonance structure here for nitromethane. We have also written here two resonating structures for benzene. So we may need to write even more resonance structures for many more molecules. Let's now see the rules that one should keep in mind while writing resonance structures. The first thing is the position of nuclei should be kept fixed. So wherever the position of nuclei, once you write one structure, and wherever the nuclei of different atoms or different elements are there, the position of the nuclei should be still there in other resonance structures as well. So the position of nuclei should be kept fixed. The number of unpaired electrons as well as unshared electrons, unpaired as well as unshared electrons in all the structures will be the same. It means if there is any odd electron, the number of odd electrons in all the resonance structures will be the same. As well as if the number of unshared pair of electrons usually also we keep, same is the number of lone pairs would also be same in all the resonance structures. The net charge on all the atoms of the resonance structure must be constant. It means if any net charge is there on the molecule, if the molecule, the entire molecule is neutral, so in all the resonating structures, the net charge must be zero. Even if you see the separation of charges, if there is a positive charge and there is a negative charge, the sum of all the positive and negative charges must be zero for a neutral molecule. Or if there is a net negative charge on a molecule or on an ion, so that net negative charge still be there. It must be there in all the resonating structure of that anion. Similarly, if there is a net positive charge on a cation and if you are writing different resonating structures of that cation, the net charge on all the resonating structures, or we also call the all the canonical structures, or all the resonance forms of that cation must be constant, it must be the same. So only the change in, then what will be the difference? The difference will only be in the location of loosely bonded electrons. And what are these loosely bonded electrons? So these electrons are pi electrons with pi bonds as well as the lone pairs. And so the position of lone pairs and the pi electrons will only vary. Rest of the things will still be fixed, it will be constant. And because of the position of the pi electrons and lone pairs vary, so you may see the separation of charges in different resonating structures, particularly if lone pair will take part in the resonance structure formation, then you will see the separation of the charges. You will see the appearance of the positive charge as well as a negative charge. So those things we'll see later on. So there are four rules that one should keep in mind. The first thing is position of nuclei should be kept fixed. So we don't change the position of nuclei while writing different resonating structures of a same molecule. And then the number of unshared pair of electrons, unshared and as well as unpaired electrons, means odd electrons, must be the same in all the structures. The net charge on all the resonance structures must be constant. Only the change in the location of loosely bonded electrons take place. And once you know how you can write how you can write the resonating structures of a molecule, then what happens is suppose you have five different resonating structures of a single of a molecule or single molecule. So the actual molecule will be the resonance hybrid of all these resonating structures. It means all these structures are in resonance with each other, and that resonance is finally what the real hybrid will be formed with the resonance of all these structures. So these are resonating structures. They are in resonance with each other, and so they will give us a molecule, the hybrid structure, which will be the real molecule, will be the actual molecule, which will behave as a real molecule. But we cannot write to the structure of that molecule exactly in the form of all the rules that set of rules that we know in terms of chemical bonds, number of bonds, and so on. So now let us look at once you know how when you can write the different resonating structures of a molecule, then what we also know that different resonating structures, their contributions towards the resonance hybrid depends on their relative stability. Suppose if there is a structure, it is most stable in all the given resonance structures, so its contribution towards the resonance hybrid will be most. So the resonance hybrid will be more likely to this most stable structure. It will more like structurally as well as chemically, its behavior will also be more closer to the most stable structure. However, if there is one resonance structure which is least stable, its possibility is very less. And so it means the resonance hybrid will be very unlikely to match with this structure, although it may have very small contributions toward the resonance hybrid. So, and depending on which structure will be more stable, and how the thing is, how will we identify which structure, and out of different resonating structures, which one will be most contributing and their order of contribution, how will we determine? We can determine it when we know the relative order of their stability. So the issue is how will you define or how will you determine the relative order of the stability of different resonating structures? So again we see a certain set of rules. These rules we follow in a certain order, and based on that we determine which structure will be most stable, and the other out of the other structures what will be their order of stability. So first rule is, so the relative stability of resonating structure should be deduced in the following order. The first is the structure will be more stable. The structure with more number of covalent bonds will be most stable. So if suppose there are two resonance structures, and if you see the number of covalent bonds out of the two structures, if one is having higher number of covalent bonds, so the one with the higher number of covalent bonds will be more stable, and it will be more contributing towards the resonance hybrid. However, if you do not see any distinct, you cannot distinguish them between just by looking at the number of covalent bonds. Then we look at the second rule, the structure with all the atoms with an octet of electrons. So we will look at those structures as these two structures, and we will see which of the structure in which of the structures all the octet of all the atoms are complete. Means they all the atoms have octet of electrons, 8 electrons in its valence shell in the given structure with all the bonding pattern that is there. So the only thing is for hydrogen we see the duplet condition. The hydrogen cannot have can 8 electrons in its valence shell. It can maximum have 2 electrons in its valence shell. So we see for hydrogen only the duplet of electrons. But for all other atoms, we see whether the octet of all the other atoms are complete or not. Then we try to distinguish or we try to determine the stability of different structure. Even if you do not see any difference, then we see a structure with more dispersal of charges. In which of the structures the charge is more dispersed? It means if there is a positive charge at one center of the molecule, we see in which structure there is a possibility of the dispersal of this positive charge more. And if there is a negative charge, in which structure you will see the dispersal of the negative charge will be more. Or if suppose even if the two different molecules or different ions are there, and two different ions, and out of these two different ions, if you see in one of the ions the dispersal of the charge is more feasible than another ion, then you will see that first ion, the ion with the more possibility of more dispersal of charge will be more stable. And this is how one determines that if that ion will be more stable, because it can have two different resonance structures where the charge will be distributed over two different atoms, and if it will be distributed over two different atoms in different structures, so the charge intensity at one place or the intensity of charge at one place will decrease, and so the structure will be more stable. As we know, the intensity, if the charge gets intensified, the stability of any structure decreases. Then the fourth point is less separation of opposite charges. And if suppose the charge of separation happens between happens in a resonance structure, and this separation is there in two different resonance structures. So what we will see, we see the in which structures the opposite charges are at the least separation, or the less separation. So if these are if there are opposite charges, and just if the opposite charges are there, and if these opposite charges are nearby, so they can actually stabilize each other, so there will be a stronger electrostatic attraction, and because of the stronger electrostatic attraction the energy of that system will go down. But if the charges, these charges, opposite charges are at the farther places, that there are distal positions, and if there are distal positions, that if they are far away at distant positions, then in that case what will happen, the distance between them will be high, and if the distance between them will be high according to Coulomb's law, the interaction between them will be lower, and thus the electrostatic attraction will decrease, and if the electrostatic attraction will decrease, the stability of that resonance structure will also go down. So the less separation of opposite charges means if the opposite charges are there, means a negative charge is there, in that case what will happen, the stability of the that resonance structure will be more. However, if there is only one charge, positive or negative charge, in that case we will see a different thing, that in that case we see the dispersal of the charge. Then the fifth rule is, even if you do not see any difference up to here, then the fifth, we look at the fifth point, and the fifth point is the negative charge on a more electronegative atom, and positive charge on less electronegative atom. So usually it should happen that less electronegative atom is the one which is more electropositive, and more electropositive atom has a stronger tendency to donate electrons, and so it can accommodate positive charge better than if the positive charge is on the more electronegative atom. So that if the negative charge is there, it should be ideally on more electronegative atom, because we know is more electronegative atom can hold a negative charge in a better way, because the effective nuclear charge is more, so the attraction of the nucleus towards this charge will be more. It will be stronger. And then the last is the negative charge on the less electronegative atom and positive charge on less electropositive. The negative charge on less electronegative atom and positive charge, let this is also be on more electronegative atom. Let us write it like this, otherwise it will be confusing. So then the fifth rule, what is negative charge on a more electronegative atom and positive charge on less electronegative atom. And then the comes will be the least stable will be the negative charge on a less electronegative atom and a positive charge on more electronegative atom. More electronegative atom would not like to have a positive charge because it is hungry for electrons, and so it will not like to have a positive charge on it. And if it is there in the one of the resonance structures, that structure will be least stable. And if you don't see any differences up to here, it means the two you don't have any. There is no difference between the two different structures, and these different resonance structures are actually equivalent structures, and usually we see in these cases, if you see these two different structures, the resonance structures, they are equivalent resonance structures. You cannot see any difference between them, and so these two resonance structures are equivalent to each other and they will be equally contributing. So their stability is also same, and so they will be equally contributing towards the resonance hybrid. And in such a case, it is very easy to write the actual bond. The actual bond between this carbon and oxygen will be around 1.5 bond. The bond order will be around 1.5, because this is also right. This is one of the resonance structure. This is one of the resonance structure. One of the resonance structure suggests that there is a double bond between carbon and oxygen. Another it suggests there is a single bond. So the real structure, the hybrid will be having around bond order around 1.5, and the similar thing will be here as well. So let us now see some questions based on whatever we have studied till now. So write the resonance structures of acetate ion and show the movement of electrons by curved arrow. So this is the structure. This structure will open it up. So this CH3, CH3, then carbon, carbon, and this carbon CO. This will be the carbonyl group. So carbon double bond oxygen, and then O minus. So there is a single bond between carbon and oxygen, and the negative charge on the oxygen atom. So this is one of the resonance structure of the acetate ion. And then we'll see the first we write the structure and put unshared pair of valence electrons on appropriate atoms. So we have written the structure and appropriate number of valence electrons or unshared pair electrons. We have put on the appropriate atom. Then this atom there will be only two unpaired electrons, two uh, pair of two pair of unshared electrons, and two pair of unshared electrons means two lone pair of electrons on this oxygen atom. So two lone pairs are on this oxygen atom, and there will be negative charge on this, and with this negative charge there will be three lone pairs on this oxygen atom. And why? Because this oxygen atom has gained one electron, and it has already, if it was in separation, it was having six electrons. Now it has gained one electron from somewhere it has taken, and so the seven electrons, and out of the seven electrons, one electron it shares with this carbon atom. So because of the sharing, it also gets one electron. The octet of this is completed, but one of the electron of this oxygen, which was having seven electrons, in this 2 minus form. So out of the seven electrons, one electron is here in this sharing, and the rest of the six electrons must be shown as a lone pair with a negative charge. because that these are so there are three lone pairs. So this is what we do. Then we draw the arrows showing the movement of electrons to get the other structures, and this arrow we draw because we know how we can delocalize how the electrons are delocalized because of the conjugation, and so that the conjugation between this lone pair and this pi electron or pi bond. And so this lone pair, if we put this lone pair, shift this lone pair between this oxygen and this carbon atom, so this negative charge will disappear because two electrons we are now putting it. Out of these two electrons, one electron is given to this carbon atom. So one can consider if there is a double bond, and so this negative charge that was there, so one electron is given to this carbon atom, so this negative charge will disappear, and out of the lone pair of electrons, three lone pairs, two of the one lone pair is now involved in the bonding. So there will be double bond. So there are now the only two lone pairs will be left on this oxygen atom. And now once it form a bond between this oxygen and this carbon atom, if the bond is all the bonds, other bonds are also inside. You will see the 5 valency of this carbon atom and 5 covalency of carbon atom means carbon will have 10 electrons in its valence shell, which is not a feasible condition because carbon is a second period element. It does not have any vacancy or vital, so it cannot expand its octet. So expansion of the octet is not possible, and so the carbon, this bond, this pi electron, this pi bond will be broken, and so both the electrons of this pi bond, the electrolytic cleavage of this pi bond will happen, and both the shared pair electrons will move on this oxygen atom, and so we get another negative, the negative charge on this oxygen atom. And with this negative charge, both electrons, it was having two lone pairs, now two electrons are again now going to this oxygen atom, so there is three lone pairs on this oxygen atom. And so these are two resonance structures of acetate ion. These two structures are equivalent. Their stability everywhere. We do not see any difference. Now the number of covalent bonds are same. The charge is electronic charge can be dispersed. In this, it can be dispersed, so this structure will be formed, and if this in this structure, it can further come here, and this negative charge will come now on here. So we will get this. So this is what we say, right double-headed arrow, and then we see the number of lone pair of electrons are also same. We do not see any difference. So these two structures are on any of these conditions, and so with these two structures are equivalent resonating structure, so their contributions towards the resonance hybrid will also be the same. And that is why this acetate ion we sometimes also write CH3, then single bond C, a single bond oxygen and single bond oxygen, and then we write a dotted line between these two oxygen and negative charge in between these two oxygen somewhere here we write. And this structure we write the resonance hybrid. This structure will be closer to the resonance hybrid, or it may appear like the resonance. It appears like a resonance hybrid. Now let's see the next question. So write resonance structures of CH2 double bond CH indicate relative stability of the contributing structure. So we'll have to write the resonance structures of this aldehyde. So we see this structure. We'll write this CH2 double bond CH already given. We will just open up this carbon, this aldehyde group, functional group. So there is a C double bond O and CH bond. So the rest of the bonding are already shown. And now we'll show the two lone pairs on this oxygen atom because oxygen is forming two bonds with this carbon, the double bond with carbon atom. So two of the electrons of the valence electrons of the oxygen are now involved in the sharing with the carbon. Now the four electrons of the oxygen will still be left, and thus it will have two lone pair of electrons which are shown here. Now, if this double bond, we see this double bond will is in conjugation with this single bond. So, if this double bond shifts here, if this one shifts here, what will happen? This carbon will have high valency. So, this carbon cannot keep high valency. So, this bond will be broken and negative charge will appear on this oxygen atom. So, and since this electron, this third pair of electrons are moving here, so the carbon atom will acquire a positive charge in that resonance structure, and that is what we can see here. So this the double bond has shifted to this position between this carbon and this carbon, and so you can see a double bond here. And because of the shifting of this pi electron or pi bond, shifting of this pi bond or pi electron, we see a positive charge on this carbon atom because one of the electrons of this carbon atom, which has shared with this carbon atom, has gone to this position, and so it will have a positive charge. And now this pi electron is now it moves to this oxygen atom. So one does both the electrons, so both the pi, this electrons that are involved in this pi bond, so they have moved to this oxygen atom. So one lone pair will increase on this oxygen atom, and the one carbon atom from here, out of these two electrons, one electron was of the carbon atom, and anyway this carbon atom has lost one electron here, but it has gained one electron here. So the net charge on this carbon atom will still be same, it will still be neutral, but this oxygen atom will become negatively charged because it has gained one electron. And so we get this resonance structure. So you can see that positions of all the nuclei are same, even if it was same in this structure, and position of all the nuclei are still same in these two structures. We have not made any changes with the positions of nuclei. What we have done is we have only changed the position of the pi electron as well as the lone pair. Here also the position of the lone pair we have changed, and here the position of pi electron as well as the pi electron, and here also pi electron position and the lone pair position is changed. Here the lone pair, the this. So now what we see, another thing will be if this double bond, now if this double bond shifts to this position. If this double bond shifts to this position, so what will happen? This carbon atom will have five valencies because one bond is here between this CH2 here, two here, so this carbon cannot have five valencies. So this bond will be broken, and this bond will be broken, it will shift to this carbon. So this carbon atom, so it will acquire a negative charge, and this oxygen, because both the electrons of this pi bond have shifted to this position, and so there will be positive charge on this oxygen atom. So a positive charge here and double bond between this carbon and this carbon you can see in the third structure, and a negative charge on this CH2 group. And thus what we so we can have three different resonance structures of this molecule, and out of these three different structures indicate relative stability of the contributing structures. We have to find out the relative stability of the contributing structure. This structure is having no charge anywhere, there is no separation of charge, and also if you look at the number of covalent bonds, so these two bonds here and two bonds here, 4, 5, 6, 7, and 2, 9 covalent bonds are there here in this structure 1. We look at the second structure 2 and 1, 3 and 1, 4 and 2, 6, 7 and 8. There are only 8 covalent bonds, 9 covalent bonds in structure 1, 8 covalent bonds in structure 2, and structure 3, 2 plus 1, 3 plus 1, 4 plus 2, 6, 7 and 8. In the third structure also the number of covalent bonds are 8 only, and so the first structure will be most contributing, and it will be most stable and thus most contributing structure. And there is also another point that this structure, there is no separation of charge. So this structure, all the atoms are not having any positive or negative charge. They are electrically neutral, and thus this structure, as per we can also say that this structure is having no separation of charge. So this will also be more stable. Then we can now we let's look at these two structures. Which one will be more contributing? Now the number of covalent bonds will not tell because the number of covalent bonds in second structure and third structure are same. Both the structures are same. So it is 8 covalent bonds here, 8 covalent bonds here. We have just counted. Then we look at the other points. We'll see at the separation of the negative and positive charges. And we can see the negative and positive charges are at the same distance in these two structures. Only the thing is the positive charge and negative charge, their positions are changed, but the separation between them, the distance between them is still same. So the positive and negative charge, their separation will not tell any of anything. So so that we can find out which structure will be more contributing out of these two. Now we'll look at the rule number 3. The negative charge on a more electronegative atom and positive charge on a less electronegative atom. So negative charge in this structure, negative charge is on oxygen, which is a more electronegative atom, and the positive charge on this carbon atom, which is a less electronegative atom. However, in the structure 3, positive charge on oxygen atom, and oxygen atom is a more electronegative atom, so it will not like this structure. This structure will be less contributing. This actually satisfies the rule number 6, and so this structure will be least contributing. This one will be most contributing than this one, and this one. Now let us look at another point. If you look at the number of lone pair electrons on the oxygen atom. In this on this atom, there are six lone pair of electrons or unshared pair of electrons. Three unshared pair of electrons means six electrons which are unshared. Six unshared electrons means three unshared pair of electrons. If three lone pairs here, only two lone pairs. There are also only two lone pairs and one lone pair is here. So the number of lone pairs we can see there is not fixed. So one thing that I have said here that I think doesn't it cannot be true. As the number of unpaired electrons in all the structures should be same. I said the number of unshared pair of electrons should also be same. This doesn't hold true. So the rule is only the number of unpaired electrons, is the number of odd electrons must be constant. So the number of odd electrons and the net charge should be kept constant in different resonating structures. It is not the number of lone pair of electrons because anyway we can understand it here somehow I made mistake because lone pairs can also take part in bonding and once the lone pair is taking part in bonding, so you may see a difference somewhere else. And so the lone pair in the lone pair is taking part in bonding here. If we start with this lone pair will take part in bond formation here, and so we see the number of lone pairs will now decrease in this structure from two to one. Anyway, so there are different ways to look into these structures, resonating structures, and so the answer is given here. So whatever I have discussed just now to find out the relative stability of these resonance structures and also their contributions. The same thing, the answer is given here. You can read it out. Let us now look into the next problem. To explain why the following two structures, 1 and 2, cannot be the major contributors to the actual structure of CH3, COOCH3. This is a methyl acetate. The actual structure, the question is, we have to explain why these two structures cannot be the major contributor, since their contributions to the resonance hybrid of this methyl acetate is very less. We have to give the reason why it is so. And if you look at this structure, the number of covalent bonds in this structure, first we will look the covalent bonds of CH3, so three covalent bonds here, and then one covalent bond will be carbon 4 and the carbon oxygen double bond 4 and 2, 6, one single bond 7, and single bond 8 and 3. 11 covalent bonds are there in this structure if we just simply count CH3CO OCH3. So 3 plus 3, 6, 7, 8, 9, 10. I think 11 is, I think it is right. Or maybe you can count, let me count it again. 3 covalent bonds here and 4, 3 and 1, 4, 4 plus 2, 6, 6 plus 1, this carbon, this oxygen, 7, and then this oxygen is 8, and 3, 11. 11 is the right one. Now the number of covalent bonds in these two structures, if you look at 3 here, and 1, 4, 1, 5, 1, 6, 1, 7, and 3, 10. There are only 10 covalent bonds in structure 1. In this structure, 3 plus 1, 4 plus 1, 5 and 2, 5 and 2, 7, and then this 8, and then this 3, 11. So the number of covalent bonds are 11 here in this structure. So the number of covalent bonds will not tell why this structure is less contributing. So, but we can find out different ways to understand. So the two structures are less important contributors as they involve charge separation. So if the charge separation is there, we have seen if the charge separation is there, that is not a stable condition for a resonance structure. And so the charge separation is happening in this structure. If we just expand, right, this is the structure in the expansion. This structure will have this all the atoms in the neutral form. The charge separation doesn't occur. So no atom has a complete positive or a complete negative charge. There might be a partial positive, partial negative charge based on the electronegativity, but there is no complete shifting of the electron. So charge separation doesn't occur in this structure. But a complete charge separation happens in these two structures, and so these structures are charged structures, and out of this charged structure, so these structures are less contributing. Another point is if you look at this first structure, you can see this carbon atom, its octet is not complete, it has only 6 electrons. It has a sextet of electrons. And so sextet of electrons, so it is less contributing because it has only 6 electrons in its valence set. Although this positive and negative charge they are separated, but they are on adjacent carbon atoms. In this structure, the positive and negative charges are not on the adjacent carbons. They are farther, they are 2 bonds away, and so the larger separation means the positive negative charge will stabilize each other less. Although the octet of all the atoms are complete in this structure, but their positive charge and negative charge are separated out, and they are separated, and also they are not at the adjacent carbon adjacent atoms. They are at the alter they are at the 2 bonds distance, and so the stability, relative stability of this structure will go down. The electrostatic stabilization will go down, so this will also be less contributing. So additionally, what we can see is structure 1 contains a carbon atom with an incomplete octet. This carbon atom with an incomplete octet, as structure 2 contains positive charge on the oxygen atom, and this structure we see positive charge on a more positive, sorry, on a more electronegative oxygen atom has a positive charge, and as the electronegative atoms don't like to carry positive charge, so this will also be having less contributions, this will be less contributing. Another point is I have seen the separation of charge is also there. So based on the different factors, different logics, you can just identify which structure will be more contributing or which one will be less. And based on their relative stability, their contributions for the resonance size will be determined as well. So the relative stability we can determine based on the structure. And once you know the relative stability, you can see their relative contribution. Let us once we know the resonance, how we can write the resonance structure and the resonance structures that about the conjugations we have also seen, and now the relative stability of the resonance structures we have also seen. Now let us look into the resonance effect, because we can have different resonance structures. So because of the different resonance formation or resonating structures, we see a certain kind of effect as well, and this effect we call the resonance effect, because this different possibility of having different resonance, possibility of having different resonating structures also has certain effect on the properties of of an organic molecule, and that effect is called resonance effect. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds, and when these two pi bonds are in the conjugation, if they are at the alternate positions, so pi bond, then a single bond, a double bond, single bond, and then again double bond. This is called the conjugation, which they are at the alternate positions or between a pi bond and a lone pair of electrons. And similarly, it can also be polarity will also be produced. You can see the polarity is produced in this molecule. This is a neutral molecule. Now, because of the resonance structures, we see a positive and negative pole here. We also see positive negative pole, a complete separation of charges, and this polarity will be produced in the molecule because of the conjugation effect or the resonance effect. And so the bond and the lone pair, if the pi bond is in the conjugation with the lone pair, pi bond, if it is also interact with a positive charge, pi bond can also interact with a negative charge or an odd pair of electron, of an odd electron. And what does it mean? If we call the condition of conjugation, if there is a double bond here and then there is a single bond, and there is another double bond here. So this double bond and this double bond are said to be conjugation. Now, if this is double bond, and at this atom was having pi electron because there are pi bond. If suppose this atom is not having a pi bond, but if it is having a lone pair of electrons, so this lone pair is said to be in conjugation with this pi electron. Even if this atom has a positive charge, so this positive charge will be in conjugation with this. And if there is a negative charge, this negative charge will also be in conjugation with this. If there is odd pair of electrons, that odd pair of electrons will also be in conjugation with this. And what does this conjugation means? Means the different pi orbitals, and if this structure could be in the plane, if this entire structure in the plane, so what will happen? These different pi orbitals, they will interact with each other in different fashion. When of, in one of the resonating structures, it will interact in a different way. In another structure, it will interact in a different way. As we have seen in this case, these structures. You see here in this structure, there was a pi and this lone pair. In this structure, let us see this structure is one kind. There is a pi bond between this carbon atom and this carbon atom. So out of the plane, there was a pi. There was a p orbital and this p orbital. These two p orbitals were now interacting here, and so there was a double bond, the pi electron. Now this we can see this pi electron is also there. So two p orbitals here between this carbon and this oxygen are interacting. What happens in the next structure, as we see here, the pi, this p orbital of this carbon atom, it is now not interacting with this, not interacting with the p orbital of this carbon atom in this structure, but it is interacting with the p orbital of this structure, carbon atom, and thus the electron from this pi orbital is shifted to this position finally. So the pi orbital actually, because of the positive or the conjugations, their positions, their interaction, different structures, it changes. Even if there is a positive charge, if there was a positive charge here, what will happen? The positive charge is an empty p orbital. And so that positive charge, the empty p orbital can be, suppose there was a positive charge on this carbon atom, it means it was having an empty p, it is having an empty p orbital. And that empty p orbital can still interact with the p orbital of this, and that in that interaction it may happen that the entire both the pi electrons may shift to this empty p orbital of this carbon atom, and that is how the interaction happens. Even if there is a negative charge on this, it means it is having a lone pair of electrons, and lone pair of electrons, and that negative charge, and this is the filled p orbital, and if the filled p orbital is there, and if this molecule, the structure of this molecule, a filled p orbital can still interact with this one. So the if the p different p orbitals are there, and if they are aligned in a particular orientation, and if they are in the position to interact with each other, if their orientation are favorable, so they will interact with each other in different possible ways, and because of that interactions, we see different resonance structures can be formed. And so that similarly, that effect is what we see in the different aromatic molecules and the many other places as well. Wherever there is conjugation, we'll see that effect. Means if there is a pi bond, pi electrons that are involved, and pi electrons means the p orbitals are there which are taking part in bonding formation, and that bonding formation, that pattern, because the pi electrons are pi bonds are relatively weaker than the sigma bond, so we see there is a delocalization of this pi electrons, and because of the delocalization of this pi bond, because of the delocalization of pi electrons, we see different kind of structures, and the polarity gets generated in the molecule. The effect, this is what the, again let me read it out. The resonance effect is defined as the polarity produced in the molecule by the interaction of two pi bonds, or between a pi bond and a lone pair of electrons, or a pi bond and a positive charge, or a pi bond and a negative charge, or pi bond and odd electron. This is present on an adjacent atom. When it is present on an adjacent atom, the effect, this resonance effect, is transmitted through the chain. As we have seen, this is transmitted through the chain. This transmission we have seen here, as well. So along this chain it is transmitted. Along this chain it is also transmitted. This effect. Now, there are two types of resonance, or these resonance effects are also called mesomeric effect. And so the two types of resonance effect or the mesomeric effects. This resonance effect is can be R effect, resonance means R effect, and mesomeric effect is abbreviated as abbreviated as M effect. So, so positive resonance effect, we can also call it as a positive mesomeric effect, and the positive resonance effect is represented as plus R effect, or the plus M effect we can also write as the positive mesomeric effect, they are same. And the negative resonance effect, we represent it as minus R effect, and the minus R effect is same as the minus M effect, means the negative mesomeric effect. Let us now look into positive resonance effect and the negative resonance effect. So the positive first, let's see first the positive resonance effect. So in this effect, the transfer of electrons is away from an atom or substituent group attached to the conjugated system. So what happens, the transfer of electrons is away from the substituent and into the conjugated system. This is the conjugated system, this is the aromatic ring, or the pi electron is conjugated system, and we see the movement of electrons in the substituent away from the substituent. And so this is called positive resonance effect. Or what we can see in other way, we see the movement of electrons into the pi system. This is the pi system, and the movement of electron moves from substituent groups into this, and so this we call as a positive resonance effect. And this positive resonance effect we see if the lone pair is in conjugation with the pi electron system. So we see the positive resonance effect. Now we see this lone pair. Now in this lone pair may shift to this position, and then the carbon will, in that case, the carbon will have 5 bonds, but the carbon cannot have 5 bonds, so it cannot break the sigma bonds because sigma bonds are more stable. So it will actually, if one pi bond formation happens here, so for this pi bond, it may compromise this to get this pi bond. It may compromise with this pi bond because the sigma bonds are more stable. There is a stronger uh, overlap between the orbitals, so they are much stronger. So the sigma bonds will not break, otherwise the system will become unstable. So we see this shifting here, and with that, where negative charge will be generated here. Now we can see the lone pair was here in this structure. Lone pair was in conjugation with this pi electron or the pi bond. How now in this structure we can see this negative charge in conjugation with this pi bond, because this negative charge is at the alternate adjacent carbon to this pi bond. This pi bond are there, and to the adjacent carbon there is a negative charge. So this is in conjugation with this. This negative charge is also in conjugation with this pi bond. So this may shift to this position, and so we'll get this structure. But this structure is already there. We will not get a new resonance structure by moving this negative charge to this position. So we have not written it. So now if we shift this negative charge at this position, because this is in conjugation with this pi bond, and now so this pi bond now will shift at this carbon atom. So and thus a negative charge will appear on this carbon atom, and thus there is a double bond between this carbon and this carbon. In the next structure, this can move back as well. So we'll get this structure, but this structure, as we are already having. So this will move this structure to this side, because this negative charge is in conjugation. The negative charge is a lone pair of electrons. The form of negative charge is in conjugation with this pi bond, and so this moves between these two carbon atoms. So this will break, this pi bond will break. So there will be an, for this pi bond between this carbon atom will compromise this pi bond. And anyway, it will not affect the stability. So this will, because it is between carbon pi bond between two carbon atoms. So this will go here. If And now we'll see a negative charge here. In the next step, what can we do? This negative charge, we can say it will be the conjugation with this double bond, and so it will move here, and this double bond will go back on this hydrogen pair, will again get back on this nitrogen atom, so we'll get the first structure back after this. So there are four resonance structures we have written here, and this resonance structure is because of the plus R effect. A plus R effect means that this is a kind of electron donating effect. It is a lone pair donating effect, and lone pair is being donated into this pi electron system in this aromatic system, and we see because of this negative charge appears on different structure, different carbon atoms at different positions. And because of this negative charge we see, when we will see the reactions of aromatic compounds, we will see the direction where the electrophile will come, because these are the aromatic molecules. They have pi electrons, and so they are actually electron rich. So the electrophile may come and attack here, but which position the electrophile will go, what we can see here. And this supposition, this carbon, there is no negative charge in any of the resonance structures. Only the negative charge appears because of the plus R effect on this carbon atom, and this carbon atom. And so negative charge density on this carbon atom, this carbon atom will be more. So electrophile will prefer to come at these three positions, and that is what we see. The electrophilic attack only happen at these or these positions, and these two positions are called ortho positions, and this position is called para position. So these such groups with the plus R effect are called ortho para directing. This is the directing ortho para directing group because of the resonance effect plus R effect of this amine group. and so on. So this electron displacement makes certain positions in the molecule of high electron density. That if you see this position, and this position, in this structure, these, and this positions are having high electron density. And if they are having high electron density, they will be attracted towards a positively charged or electron deficient species, and so a certain reaction will happen. Which now let us look into the negative resonance effect. So this, yeah, one more point here. Let me discuss. If the planarity, if somehow you disturb the planarity of this group, then what will happen? These different p orbitals, which is there in conjugation, now their orientation will disturb because of the planarity. If there was planarity, if the molecules, everything was in planar, so all the p orbitals will be perpendicular to the plane of this screen. So they are all perpendicular to this, and thus they are actually parallel to each other. They are oriented in such a fashion that there will be maximum overlap between p orbitals. Suppose if somehow by certain effect, if I add certain groups and the planarity of this engineering, if suppose I disturb, if this planarity is disturbed, then what will happen? The different conjugation will also disturb, because now the p orbitals will be oriented, disoriented, and once they will be disoriented, there will be no proper overlap between them, and if there is no proper overlap between them, that is what we say the conjugation will be broken, and so we cannot write different resonance structures in that case, and that is sometimes people do. This is called steric inhibition of resonance. People add some steric groups, larger groups, and because of that larger group steric effect, the this planarity disturbs, and so the what we have the we say that we call it as the steric inhibition of resonance, and that effect we'll see if it is. I'll see if it is there in your syllabus or not. If it is there, I'll also put and explain it to you. Let us now look into the negative resonance effect. The negative resonance effect is also, it is shown as minus R effect. It can also be written as minus M effect, as a negative mesomeric effect. So this effect is observed when the transfer of electron is towards the atom or substituent group attached to the conjugated system. Means the transfer of electrons happens towards the substituent. Means from the pi electron system or the pi bonded system, electron rich system, the electron moves towards the substituent group, then that is called the minus R effect. Means this is the kind of electron withdrawing effect. And in this electron withdrawing effect, we see the electron withdrawal of, means the withdrawal of pi electron. In we have also seen electron withdrawing group, electron withdrawing effect as minus I, and electron donating effect as plus I. In that case, what we have seen the electron density donation to sigma bonds. Here we see this electron withdrawing and donating effect to the dispersal of the pi electron. This pi electron is being dispersed, and in this dispersal, what we see, this pi electron is now moved towards the nitro group in the structure. Nitro group, so it has gone in this direction, and this pi electron is only shifted. In this structure, we have seen the dispersal of this lone pair of electrons into this system. So it was moving from the electron pairs, or electron density was moving from substituent to the pi conjugated system. And now in the plus R effect and the minus R effect, we see the movement of the pi electrons away from the conjugated system, and towards the substituent. And this is what we see. There is a lone pair of there is a pi bond between this nitrogen and this oxygen. This is nitrobenzene. This was amine. This is aniline. This is one of the amine. So this is the aniline aromatic amine. So this is aniline. This is nitrobenzene. In the nitrobenzene, this bond one can also write as N, or single bond, and then there will be negative charge on oxygen, positive charge on this nitrogen. Otherwise, we can also show it as a coordinate bond. Now let us see, there is a double bond between this nitrogen and this oxygen, and there is a double bond here. These two bonds are in conjugation with each other. Now in the minus R effect, you usually see the double bond is in conjugation with the double bond, but at the end of this double bond in the substituent, we see there is a electron withdrawing group or the more electron negative group. And because this more electron withdrawing group or more electron negative group, which has tendency to pull away electron density towards itself, so it can also pull away electron density of the pi electron. And so once it pulls away pi electron and it keeps this pi electron on its own, then what will happen at a pi electron which is here, so this will shift to this position. What does it mean is this the p orbital of this nitrogen and this carbon atom. Now in this structure they are now interacting with each other, and we see there is a double bond between this nitrogen and this carbon atom. But as this p orbital of this carbon atom is now interacting with this nitrogen atom, and then what will happen? This carbon atom, its p orbital will not be able to interact with this one, and so what will happen? This bond will be broken. But this bond is broken with certain effect. We see this is an electron withdrawing effect. And so the both the this shared pair of electrons now goes into the empty p orbital and p orbital of this oxygen, and it is now having a lone pair of electrons in it. Then it goes into the empty orbital. So there will be see positive charge. Now this positive charge in this structure. Here we show negative charge in conjugation with the double bond and the lone pair in conjugation with the double bond. In this structure, what we see, the pi bond is in conjugation with the pi bond. And then here what we see, positive charge is in conjugation with a pi electron. This positive charge is also in conjugation with this pi bond. So this pi bond will shift here. So then what will happen? This electron will move here, this pi bond will move here, and we'll get this structure back. But this structure is we have already written, so we'll move to some try to find out some other structure, and those structures is what will happen. Now this p orbital, this pi bond will shift to this between these two carbon atoms, and it shift to these two carbon atoms. What there will be positive charge on this carbon center, and a pi bond will now shift to these two positions, and negative charge is already there on this oxygen. Now this positive charge again in this structure is in conjugation with this. It was also in conjugation with this, but we get back to this position. If this is in conjugation with this and this pi bond shifts to between these two carbon atoms, so we will get this structure, and this positive charge will move in this direction. So what we see in the direction, positive charge moves in the direction, in the opposite direction to the movement of the other, to the direction of the delocalization of the pi bond in minus R effect. In the plus R effect, we see negative charge moves, but negative charge moves in the same direction in which the delocalization happens. Delocalization of the pi bond happens. But in the minus R effect, the delocalization of positive charge in the opposite direction of the delocalization of the pi bond. Now this cross charge will move here, and the pi electron, this pi bond shift to between these two atoms. Now in the next structure, what will happen? This positive charge will move here, this will go back to here, but this will go back to, so this, there is a negative charge here, so this negative charge will move here, this positive charge move between, this pi bond will move between these two carbon atoms, and this carbon positive charge will disappear, and this negative charge has moved here, so this charge will also disappear, we will get the first structure back. So what we have seen till now, so there are two types of plus and minus R effects, and based on the substituents, we also see the substituent. What we see, because of this minus R effect, we see a positive charge is intensified at certain positions, and these positions are also at para positions itself. Here we see with the plus R effect intensification of negative charge at the ortho and para position. Here we see positive charge gets intensified or it appears on ortho and para position. So electrophilic attack will not be favored if the electron withdrawing group is there. Mm, Electron withdrawing group is attached to the benzene ring. Electrophilic attack will not be favored at the ortho and para positions, because this position, this carbon atom now will see some positive charge effect on it. There will be some positive charge density because of these resonance structures, because all of these structures have certain contributions towards the resonance hybrid. And how much contribution they will have, it will depend on the relative stability of all these structures. Up to here, these three structures are equivalent structures. This structure will be most contributing, this structure will be most contributing, the number of pi electrons are maximum in this case, and also that there is no charge separation in this structure, but this structure will also be, these structures will also have certain contributions here also. Again, even if because of certain substituent, if it is added at certain positions, and if you disturb the planarity of any group or the planarity of the nitro group, we can easily disturb. So suppose if I add a very bulky group here, then what will happen if bulky group I add here, so that bulky group will interact with this oxygen. So what will happen? This nitrogen, which are this NOO group, which was in plane of this benzene ring, now it will go away of the benzene ring, and so it will become perpendicular to the benzene ring. Once it will become perpendicular, means this oxygen atom will come above the plane, and this oxygen atom will go below the plane, and the rest of the things are in the plane of the screen. Then you will what will happen? The pi bonds of this pi bond will not be in conjugation with this pi bond, even though these two pi bonds are at the alternate position, and that is what is called the steric inhibition of resonance. I have just explained it again. So suppose if I add tertiary butyl group here, so the steric inhibition of resonance will happen here. The atoms are substituent groups which represent plus R or minus R electron displacement effects are as follows. So the plus R effect we see it will be shown with the substituents which are having a lone pair of electrons at the atom which is attached to the benzene ring or the pi electron system. And so the like the aniline, then NH2, we see the OH group. This will also be having oxygen which is attached to the pi electron system. Is having a lone pair of electrons. Halogens also have lone pair of electrons. OR group, this oxygen has a lone pair of electrons. This OCOR group, the acetate group, this oxygen atom is having two lone pair of electrons. And O2 then CO is here. This is not carbonyl. This oxygen is not involved in the carbonyl bond. The carbonyl group is this one. This is actually a alkoxy group. So there is a lone pair, so it will also be in conjugation with the pi electron system, and that lone pair may shift into the pi electron uh, portion of a molecule, and so there is a pull of R effect. NH2 we have already seen. NHR in R group we replace one of the hydrogen with alkyl. In R2, NHCOR even the amide group if it is there. Although so because of the amide, the CO group, the lone pair of this nitrogen will also be in conjugation with this carbonyl group. Similarly, here this lone pair of this oxygen will also be in conjugation with this carbonyl group of the ester. But this lone pair may have been in the conjugation with the other pi, the portion of the pi electron, the region of the molecule, and so pi electron rich region of the molecule, and so we see that. Similarly, alkyl groups are also considered to have plus R effect, and the plus R effect in the case of alkyl group may happen because of the steric, because of the hyperconjugation and so on. And what is the hyperconjugation effect? We will see with later in the next class. So what we see here, a lone pair of electron in conjugation with the pi system usually. And in the minus R effect, what we see, minus R effect, there is electron withdrawing group and the carbonyl group. So we see at the terminus of this conjugation, pi electron system is in conjugation. This is a pi electron portion, and this pi electron portion carbonyl group is in conjugation with another pi bonded system, like you can see here. Similarly, we can also write this carboxylic, this NO2 group we can replace with the carboxylic acid group. And in that case, the carboxylic acid, carbonyl group of the carboxylic acid will be in conjugation with this system as well. So there is a pi-pi conjugation in this group, but in that pi-pi conjugation, what we see, there is one electron withdrawing group at one end of this substituent, and the end substituent ends with the one electron withdrawing group. In that case, minus R effect will be very effective. And so the similarly this CHO group, then this CHO group means the aldehyde group if it is attached to benzene ring or any pi electron system, or the this ketone group or the cyanide or nitro we have just seen. So these are just minus substituents with so minus R effect. Minus R effect is a kind of electron withdrawing effect, and plus R effect we are seeing is a kind of electron donating effect. The presence of alternating single and double bonds in an open chain or cyclic system is called a conjugated system. We have just seen examples are 1,3-butadiene, they are conjugated system. Aniline, nitrobenzene, aniline and nitrobenzene we have just seen. This is aniline, this is nitrobenzene. And in such systems, the pi electrons are delocalized. And we have seen delocalized means pi electron changes its position. It is delocalized. It is not fixed at one position. It is a continuously in motion. And so it is called delocalization. And in such systems, pi electrons are delocalized and the system develops polarity. And because of the delocalization of the pi electrons, system develops polarity, and the systems often show abnormal behavior. And what does it mean? We will see when we see the reactions of aromatic compounds later on. I'll stop this lecture here and we'll see in the next class electromagnetic and